Good morning, class. I want to welcome you to Chemistry 121, Introductory Chemistry 2. The last time we met, we were looking at the principles of writing Lewis structure. And while we were looking at it, I mentioned to you that in writing Lewis structure, there are some exceptions, especially for those cases where octet rule fails. So we want to today look at resonance structures, exceptions to octet rule, and how to determine and calculate formal charges. Once again, my name is Dr. Folusho Agumbiade. The principles that guide writing of resonance structure is what we'll be looking at. Now, you have a resonating structure, a resonance structure, when you have a case of electron delocalized. And what do I mean by that? If we want to write the electronic configuration of the Lewis structure of ozone, for instance, in writing the Lewis structure of ozone, you will see that you have oxygen established as the center atom, which is this oxygen. Then, if we calculate the total number of electrons on valence of oxygen, you have 6 times 3. Each oxygen atom has 6 electrons in the valence shell, and that will give you 18. Now, that 18 is what we will now look at. How do we share it in the structure, in the resonance structure of oxygen? So if we decide to go by the structure in the left, which is this one, what I'm going to now do is position the oxygen in the 3 positions as presented. So you have oxygen, the central atom, then the terminal atom of oxygen. Now, we know that oxygen will always need 2 electrons to complete its valence shell because it has 6 electrons. To get to octet rule, then you will need 2 electrons. So between oxygen here and oxygen here, we will draw a bond. And between, so we have 18 electrons. So let me try and do what I'm trying to explain. So you have this oxygen, that oxygen, that oxygen. So here now, there is a bond and there is another bond. Now, the two bonds that we have, we are going to be using those 2 bonds to determine. Sorry, I have a background noise and I want to remove the noise. So sorry for that little distraction. There was a background noise that I needed to remove. So in drawing the Lewis structure, you will see that you have your oxygen that we have put at the center, and you have your oxygen that you have put at the center, and you have another oxygen that you have put at the edge. So you have the central atom as presented, the central atom. Then you have the atoms by the terminal, which are the 2 oxygen as presented. Now, to join the 2 of them, we have 8 electrons that we want to distribute. So 1 electron, you have that bond, that single bond here, and you have this single bond here, making 6 electrons. So let me clean this so that it will be clean. So you have that bond, and you have that bond, making 4 electrons out of these 8. So we have 14 left. Now, to be able to account for the 14, let's try and distribute the valence electron, the non-bonding electron on each. Now, you have already 4 used, so we are looking for the remaining 7 pairs. So we have 1, 2 lone pairs, then 1, 2 lone pairs to make. So let me use a red ink to be able to differentiate. So I'm going to clean the blue ink and use the red ink. So you have 1, 2, 3, 4, 5, 6. That makes, that is a complete 8 on that. Then I will also probably do 1, 2, 3, 4, 5, 6. I'm just doing a hypothetical situation. You have another 8 on that. Now, if you look at this, is 1, 2, 3, 4, 5, 6, 7, 8. Let me count with a demonstration. You have 1, 2, 3, 4, 5, 6, then 7, 8 bonding electron, 9, 10, 11, 12, 13, 14, 15, 16. So 15, 16, then you will have to now put the remaining 2 electrons on this oxygen. The remaining 2 on this oxygen, 1, 2. Now, if you look at this structure as it is, there's a problem with it. And what is that? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. That is 8 electrons on this oxygen. This oxygen here. Then if you count this, 1, 2, 3, 4, 5, 6. So that this oxygen is deficient. This central oxygen is deficient. And we have already mentioned that once you see deficient electron or deficient system, it means that there is a double bond. So this bond here, this lone pair here, I'm going to put it here. So once I put it there, the meaning is that I will now have two bonds of, I'm going to have 2 bonds of commonplace. I will have 2 bonds there. Then if you now count the lone pair of electron, the lone pair of electron then becomes 1, 2 as presented here. So if you count the number of electrons on each now, you will see that it's complete. This is 1, 2, 3, 4, 5, 6, 7, 8. Now that 8, 1, 2, 3, 4, 5, 6, 7, 8. So 4 bonding electron, 4 unbonding electron. That makes this one complete. Also here, 1, 2, 3, 4, 5, 6, 7, 8. So each of them are complete. This also here, 1, 2, 3, 4, 5, 6, 7, 8. So the structure 1 is correct. But following the same explanation, this structure is also correct, meaning that you have the two correct Lewis structure for the same molecule. Now, 2 correct Lewis structure for the same molecule is telling us that there is a resonance, meaning that the electron is not localized on that position. The electron is moving from one position to the other. Now, how do we then explain that? So if we go to the next slide, you will see what I am trying to then explain. Now, in the next slide, Sorry, please, the slide is not moving. Now, in this next slide, you will see that what it means is that the electron that's supposed to be on this position, the electron that's supposed to be on this position is moving from the bonding pair here and is moving and becoming a lone pair. And when that happens, the lone pair here moves and becomes a bonding pair. So you will now have this formed. This is formed from that, this movement produced that. Now, at the same time, this bond can become a lone pair, and this lone pair can become a bond. So you will now have what is the correct thing is that oxygen, just a minute. You have oxygen, oxygen, oxygen with with the bond resonating like that. The bond is moving from one oxygen to the other. So you have a resonance structure like you have in a benzene ring. Now, in a resonance structure, if you look at this example, this oxygen is labeled A, this is labeled B, this is labeled C, A, B, C. In each of these cases, the number of electron is complete. The octet rule is achieved, but there is this electron is not localized. This electron is delocalized. It's moving from one oxygen to the other. Here it is between A and B. Here it is between B and C. So resonance structure have the same relative placement of atom, but different location of bonding and lone pair of electrons. So the positioning of the bonding electron is not the same, and the non-bonding electron, the lone pair of electron and the bonding electron moves from one place to the other. And when you have a situation like that, you will say that you have a delocalized electron system. So in a delocalized electron system, you will see your electron, your bond is resonating, is moving from one atom to the other. So it's always drawn with this example or with this model. In drawing a delocalized electron of this type, what that means is this. You have oxygen, oxygen, oxygen. In this position, there is the bond order here is not going to be 2. Neither here will it be 2, because the electron, the bond is shared by the 3. So in this case, you have a system that is resonating, and how you know that it is resonating is that you have fractional bond order. So how do you calculate the bond order of a resonating structure? You calculate the bond order of the resonating structure by dividing the number of electron pair, take note, pair, not just number of electron pair, by the number of bonding atom here. What does that mean? The number of electron pair here is 1, 2, 3. You have 1, 2, 3. 1 bond, 2 bond, 3 bond. So those are the bonding electron pair. So number of electron pair is 3 divided by the number of the bonded atom pair. You have, this is a pair of bonding atom. This oxygen to this oxygen is a pair, and this oxygen to this oxygen is a pair. So these 3 divided by 2 will give us a bond order of 1.5. So the bond order of ozone is 1.5. The bond order of is 1.5, which means that it has between 1 and 2 the strength. In previous class, Dr. Abayomi taught you that the strength is directly proportional to bond order, meaning that a single bond will be of lower energy than the double bond. A double bond will be of higher energy. So there is a direct proportionality between the bond order and the bond strength. In this case, this is going to have 1.5 bond order. So which means that the bond strength is between the energy of 1 and the energy of 2. So if the energy of 1 is 10 and the energy of 2 is 20, it means that the energy of 1.5 will be 15. So it's in between the two bond strengths. And don't forget also that the bond length is inversely proportional to the bond strength or to the bond order, meaning that as you increase the bond order, the bond length reduces. So in exam, if you are asked which of the following has a higher bond length, and we start to give you, you may need to know what is their bond order. So if ozone is there and oxygen is there, oxygen will have a double bond, which is bond order 2, but ozone will have bond order 1/3. So the bond order of ozone will be lower. The bond strength of ozone will be lower than the bond strength of oxygen, because oxygen has a bond order of 2. So in any case, in writing resonating structure, you need to consider that information and the implication on the bond strength and the bond length. Now, the next thing that we want to look at is another example of an atom that is also a resonating atom, but in this case is between 4 atoms. Now, you have nitrate ion, NO3 minus. In nitrate ion, which is NO3 minus, the nitrogen is from the way it is written, you know that the central atom is nitrogen, while the terminal atom are the oxygen. So you have your nitrogen as presented, and you have your terminal atom presented on it. Now, for us to be able to know the total number, you know that the principle of writing formal charge, principle of writing, not formal charge now, the principle of writing the principle of writing the Lewis structure is for you to first calculate the total number of valence electrons. Nitrogen has 5 electrons, so times 1. Oxygen has 6 electrons, times 3. So then, being that it is -1 raised to power -1 nitrate ion, then you have that -1, making a total of 24 electrons. Now, those total of 24 electrons can then be written in this form. So nitrogen will be in the center, and you have 1 bond, 1 bond, 1 bond. So you have nitrogen bonded to oxygen, oxygen, oxygen. Now, this is 2 electrons. This is 2 electrons, and this is 2 electrons, making a total of 6 electrons out of 24. So you have 18. So you have 24 electrons minus that. You have 18 electrons left. Now, those 18 electrons is what we want to now distribute. So I'm going to distribute the remaining 18 electron. And in distributing the remaining 18 electron, I will start with, let me start with oxygen. If I start with oxygen, I have 2 here. So I will need 6 more. So I have 1, 2, 3, 4, 5, 6 to make a total of 8 electrons on that oxygen. Then I will say 1, 2, 3, 4, 5, 6 to also make another 8 electrons on that oxygen. Now, if I go to this, I'll have 1, 2, 3, 4, 5, 6. Now, to make 8. Now, I have 8 here, 8 here, 8 here. That is a total of 24. But nitrogen here, if you look at nitrogen at the center, let me use another color to draw to so that the nitrogen here has 6. So this nitrogen has 6. So that means that we have a deficiency of 2 electrons. And anytime you have that deficiency, the implication is that there is a double bond in the structure. So how do we then address that problem of the double bond in the structure? So if you look at this that is already on the slide, you will see that the nitrogen that you have here has 1, 2, 3, 4, 5, 6. So it has three bonding pair, which is 6. It's not complete. It's supposed to be 8. So that means that there is a pair of electron that is the unsaturated, I mean, that is a double bond. So here now, if you look at this is now the double bond as presented. Now, but if you look at this double bond, you will see that it is complete. You have 4 pairs of electrons, bonding electron around nitrogen, making a total of 8. You have 2 pairs of bonding electron and 2 pairs of lone pair, making 8. 1 pair of bonding electron and 3 pairs of lone pair, making 8. 1 pair of bonding electron and 3 pairs of lone pair, making 8. So this is complete. Now, but this structure can move from here to here and from here to here, meaning that this bond, this double bond, is resonating between the atoms. So it's also a resonant structure, all of them completely fulfilling octet. So in this case, you see that octet is complete, octet is complete, octet is complete for all elements. Now, when you have this kind of resonating structure too, you have to now look at what is his bond order. For you to know the bond order, you have four electron pairs, bonding pairs. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So you have 4 bonding pairs, and you also have 3 bonded atom pair. This is with 1, 2, nitrogen to oxygen, nitrogen to oxygen, nitrogen to oxygen. So 3 bonded atom pair and 4 bonding electron pairs. You have 1, 2, 3, 4 as mentioned. So the bond order of this is 1 1/4, 1 1/3, and 1 1/3 means that it has 1/3 extra of the bond strength of the 1. So if the bond strength of 1 is 12, then that means that the bond strength of 1 1/3 will be 16. 1 1/3 is 12 divided by 3, which is 4, and added to 1. So you have that as your molecule as presented in the diagram. So what does this then mean? What are the implications of what we are talking about? What this means is that when you have a molecule and the molecule is resonating, their principle or how to write their formal charge is, I'm not talking about formal charge, how to write their Lewis structure is different. Now that brings us to formal charge. Now, when you have structures that resonate, each of the atoms in the structure, you can calculate what we call the formal charge. So the formal charge is the charge an atom would have if all electrons are shared equally. And the formula for formal charge is presented on the slide. This is a formula for calculating formal charge. In determining formal charge of an atom, each of the atom, you calculate the formal charge of each of the atom is equal to the number of the valence electron minus into brackets the number of the unshared electron plus half of the number of the shared electron. What does that mean? Let's start with atom A, the oxygen A. If you look at the oxygen atom A, the number of the resonance of A, I mean the formal charge of A will be equal to the number of the valence electron. On this oxygen, you have 1, 2, 3, 4, 5, 6. Oxygen has 6 valence electron, as in not what is A now. Oxygen has 6 valence electrons, so that's the number of valence electron, minus the number of the unshared electrons. So for this one, you have 1, 2, 3, 4. That is the unshared electron. 4 of it. Here, you have 1, 2. Here, you have 1, 2, 3, 4, 5, 6. So this one have 6, this one have 2, and this one have 4. But we are looking at this for now, that of Hay. So in calculating the formal charge of this, you will say 6 minus into bracket total number of unshared electron, which is 4, plus half of the total number of shared electrons. So this is a shared electron, the pair, the bonding pair. So 2, 2, that's 4. So making 4 here. Now, if you calculate this, you have 6 minus 4 plus 2. So that is 6 minus 6, making 0. So for this atom, the formal charge is 0. Now for B, the formal charge will be, let me go to the next slide for you to see what the formal charge will be. Now for B, the formal charge will be 6. How do we come about 6? 6 is the total number of valence electrons. So you see that ABC, 6 is the, so 6 is the total number of valence electron minus into brackets, then unshared electron, which is 2, then plus half of the shared electron. So this is 1, 2, 3, making 6 shared electrons. So you have this. Now that gives you a formal charge of plus 1. Then for C, you have 6 minus the unshared electron, 1, 2, 3, 4, 5, 6. So 6 minus half of the shared electron. The shared electron is 2. So you have 2. So you have 6 minus 1. So that's minus 1. On the basis of this, we can then write that the formal charge of this is, you have 0 plus 1 minus 1. Using the same expression, this is minus 1 plus 1, 0. Now, that is how to calculate formal charges. Now, in calculating formal charges, there is something important that we want to use that to achieve. And what do we want to use it to achieve? We want to use it to achieve which configuration of a resonating structure is the stable configuration. So you want to look at choosing the more important resonance form. Which one is more important? Now, the following are the rules. When you want to choose, when you have 3 structures or 2 structures or whatever number of resonating structure you have, or for a Lewis structure, I mean, you want to find out which of them is the stable and the preferred. Now, the following are the principles. Number 1 is that the smaller formal charge, which is the smaller positive and the smaller negative, is preferred to the larger one. What does that mean? If you have a molecule and the formal charges are +2, +1, or -2, -1. Now, this is a smaller formal charge. This is a smaller formal charge because +1 is smaller than +2. Then -1 is smaller than minus 2, meaning that when you have a structure that's, when you write its formal charge, it has plus 2. This is not preferable. When you have minus 2, this is not preferable. But this and this are preferable when you are looking at formal charges. So in short, what this means, what the first 10 sentence mean, is that when you want to choose a formal charge, when you want to choose a structure, a Lewis structure, the one with a smaller formal charge is preferable. Now, the second rule is that the same non-zero formal charge on adjacent atoms are not preferable. So let me use an illustration for that too. Now, if I have atom A, B, C, and when I calculated the formal charges, I now got that this is -1, -1, 0. Now, because they are the same formal charges, following each other like this is not acceptable. But if I have A, B, C, and I have -1, 0, -1, this is acceptable. This is acceptable, but this is not acceptable because of this -1, -1 adjacent to each other, instead of them to be far away from each other like I have here. So in any case, when you are looking, when you are doing formal charge and you are looking at what happens in formal charge situation, the same non-zero formal charge on adjacent atom are not preferable. So avoid light charges on adjacent atoms. But if I have A, B, C, if it is -1, +1, 0, this is still okay because they are not the same charges. They are not the same. They are not both negative or both positive. So in any case, you avoid positive, positive or negative, negative with each other. Then the third rule is that a more negative formal charge should reside on a more electronegative atom. Now, let me explain what that means with specific. If I have carbon, oxygen, hydrogen, for instance. Now, out of these three, oxygen is the more electronegative. So, if I have -1, +1, 0, and I have another structure of the same carbon, oxygen, hydrogen, but this one, I now have +1, -1, 0. Now, out of these two, this is preferable and this is not preferable. Why? Because oxygen is more electronegative than carbon, and oxygen is now carrying positive here instead of it to be carrying negative. Because what the implication is that a more a more negative charge should reside on a more electronegative atom. So I position my oxygen with my oxygen should because it's a more electronegative, is the one that should carry the negative charge and not the carbon or the hydrogen. Now, having known all these rules, let's see specific examples that we can use to explain and illustrate the rule. Now, there is this NCO minus. NCO minus. Based on what we have learned, we can write the Lewis structure as presented on the slide. You won't need to go and try your hands on writing the Lewis structure. But we know that carbon is the central atom, and carbon being the central atom because is the least electronegative. Then if you then want to write its formal charge, I mean you want to write its Lewis structure, the Lewis structure can be any one of these three. So you have this as a possible Lewis structure, this as a possible Lewis structure, and this as a possible Lewis structure. And they have resonating bonds. There are two bonds that are resonating. You will see that two of these bonds are presented here to make three bonds, but two of them has moved here and here. Then the two of them has moved here. So you have a resonating, you have two pi electron resonating between the three. Now, if you now look at it critically, we want to select which of these three is acceptable. Which of these three is the acceptable resonance structure or the stable resonance structure? Now, this one is out of it. This is out of it. And the reason why this is out of it is because of this positive 2. The number one rule that is presented here is that you don't want the number one rule as presented here is that you don't want big formal charges. You want smaller formal charges. And if you now look at the number 2, I mean the structure number 1, you will see that the formal charges as +2. So that one is out of it. Then the second rule is not applicable because you don't have any two positive charge or any two negative charge adjacent to each other. So the third rule is that the negative charge or the charge should be on the more electronegative. If you look at this structure, you will see that oxygen is more electronegative than nitrogen. Oxygen is more electronegative than nitrogen. So this is also out of it because nitrogen is carrying -1, but here oxygen is carrying -1. So oxygen should carry -1 because it is more electronegative. So at the end of the day, the resonance structure 3 is the most stable, is the one that is most preferred. And the reason why it is the most preferred is because of the rule that its oxygen here is carrying the higher electronegative structure. So, I mean, charge, formal charge. So in calculating formal charge, that is how to go about it and its implication. Now, the next thing we want to look at is there are some molecules that do not follow octet rule. There are some molecules that do not follow octet rule. They have exceptions to octet rule. Number one class of such molecule are molecules with electron deficient atoms. Molecules with electron deficient atoms. Now, if we want to write the Lewis structure of beryllium chloride, this is beryllium dichloride. Now, beryllium dichloride, beryllium will have two electrons in its valence shell. So you have Be having 2 electrons, and chlorine will have 7 electrons times 2. So you have +14, making a total of 16 electrons. Now, the 16 electron, I now want to distribute the 16 electron on the valence. I want to distribute the 16 electrons. So what do? I have barium as a central atom. I will join the two chlorine to it and establish their bond. So you have this bond and this bond. So this bond now is 2 electrons, 2 electrons. So I have already spent 4 out of the 16 electrons. So I have 12 electrons left. Now, the 12 electron that is left, how do I then distribute those 12 electrons? The 12 electron that is left, I will then distribute them on the nitrogen. I mean on the chlorine. So I have this. I have this. I have this. And I have this, making a total of 6. Then I have also, let me use another color. I have also this, and this, making a total of 12. So I've used up all the 16. Now, I haven't used up all the 16. Let's now go to beryllium. Beryllium has 4. It does not have 8. For normally, if it is octet, if it's obeying octet, beryllium should have 8. But if you look at the others, you will see that chlorine has 8. 6 non-bonding and 2 bonding. 3 lone pairs, which is 6 non-bonding, and also the chlorine here. But the beryllium does not have, so the beryllium did not obey octet because it has electron deficient atom. The same thing with boron trifluoride. Boron has boron has 3 electrons in its outermost shell. So you have 3 plus 7 times 3. That is for fluorine. That is 24 electrons too. So you have 2, 2, 2, making a total of 6. So subtract 6 from here, you have 18. So at the end of the day, the 18 is distributed around the fluorine, 666. So you have 6 pairs of electron there. 3 pairs of electrons, 6 electron there, 6 electron there, making a total of 18. So all the electron has been used up, the 24. 3 pairs, that's 6, making 24. So all the electron have been used up. And fluorine, all the fluorine are complete. Each of the fluorine, this one has 8 electron in her, 8 electron in her, 8 electron in her, but this one has 6. So boron is also electron deficient. So in that case, you have an electron deficient system. The other is for you to also have the odd electron species. Odd electron species. In the case of all electron species, you also have a breakdown in octet rule. Octet rule is not obeyed in odd electron species. Now, if you look at the nitrogen dioxide here, this nitrogen has, if you write its Lewis structure, you would see that in writing its Lewis structure, you have nitrogen having 5 electrons, oxygen having 6, and 6. So 5 plus 12, that is 17. 5 plus 12, 17. If you write the nitrogen and you put the bonds, you have the nitrogen, you put the triple bond, you have used up 6 out of the 17. It remains 11. So the 11 can then be written as lone pair here, lone pair here. So with this oxygen now, it's complete. You have 1, 2, 3, 4. That's 8. Then for this, you have also 2 electron, 2 electron, 2 electron. You know, we are distributing 11 electron. 4 has been sent here, 6 has been sent here, making a total of 10. Then the remaining one, you see it on nitrogen. Now, the remaining one that is on nitrogen is an odd electron species. And if you look at oxygen here, it is complete. How is it complete? You have you have oxygen 1, 2, 3, 4. That is 8 electrons. But if you now look at nitrogen, you have 1, 2, 3. That's 6 plus 1. That's 7. It did not get to 8, which is octet. So it fails because you have a radical ion that is there. And it's also a resonating structure. You can have your that electron moving from that pair, the single electron here, you have it having, a lone pair there. And the oxygen will now have the odd species. So these are two examples of situations where octet rule is not obeyed. The third example, which I was trying to also mention when I was taking you through the third example, which I also mentioned when taking you through the Lewis structure drawing, is when you have an expanded valence shell. When you have an expanded valence shell, this occurs when you come to the third row of the periodic table. In the periodic table, you have hydrogen, you have helium. Those are the first row of the periodic table. Then you now have lithium, and you have neon. So you have, let me write this properly so that we'll be able to see what I'm trying to say. You have lithium up to neon. Then you have sodium up to argon. Sorry, shouldn't have G. Up to argon. Now, in this row, elements that are in this row from elements that are in this row, which is the third row of the periodic table, because they are very close to the d orbital. Because after the element 20, you have 3d orbital. Now, 3d orbital can take electron. We would explain this further in valence shell electron pair repulsion theory. 3d orbital has empty shell that can take electron. And because of that, it is possible for you to have electron promoted into the 3d orbital. And because they are promoted into the 3d orbital, you can have more than 8 electrons in a molecule, a central atom. Now look at this phosphorus. If you look at this phosphorus very well, you will see that it has 5 bonds. This is PCl5. It's a molecule. Now this PCl5 has 5 bonds, and if you count the 5 bonds, you have a total of 10 bonds, 10 electrons in phosphorus. Those 10 electrons in phosphorus is telling us that we have an expanded valence, and it has violated octet rule. Octet means only 8, but here we have 10. Also, look at this sulfur. You will see that it has 6. 1, 2, 3, 4, 5, 6. 6 bonds to that sulfur. That 6 bond will translate to 12 molecules, or 12 electrons. And the 12 electrons violate octet rule. That's supposed to be just the 12 octet rule that's supposed to be just 8. So in summary, you can have a number of molecules that does not follow octet. For instance, here these molecules mentioned, presented on this slide, they all do not follow, they all do not follow the rules of octet. Sulfur here, as you see here, it has 1, 2, 3, 4, 5, 6 bonds. And those 6 bonds, they are electron pair each, making a total of 12 electrons. And that has violated octet because sulfur can experience expanded structure. Then you will also see the case of phosphorus here. If you look at the case of phosphorus here has 1, 2, 3, 4 bonds, and the phosphorus can resonate into that form, and you have 1, 2, 3, 4, 5, making a total of 10 electrons in the valence, and 10 electron violates octet rule. That's supposed to be a total of 8. And finally, in this example, you have electron deficient system. Let me quickly move on to a principle that will explain the valence shell electron pair repulsion theory. I will just introduce the principle, and on Wednesday we will take our time to in better details discuss it. Valence shell electron pair repulsion theory is used to interpret or to predict or to explain what the shape of molecules are. When Dr. Abayami was teaching you covalent bond, one of the properties of covalent bond that he must have mentioned to you, which is correct, is that covalent bonds are directional. Covalent bonds are directional. Now, if I want to write the structure of water, I will write the structure of water like this. There is a reason why it is written like that. If I want to write ammonia, I will write ammonia like this. There is a reason why it is written like that. And if I want to write carbon dioxide, I will write it like this. It will be wrong for me to write water like this, and it will be wrong for me to write carbon dioxide like this. So these are wrong because of valence shell electron pair repulsion theory. That is wrong. This is wrong. But this is correct. This is correct. This is correct. Because covalent molecules are directional, and their direction is explained by valence shell electron pair repulsion theory. And it is now the basis, the reason, what we've been looking at, and under the violation of octet rule are better explained by valence shell electron pair repulsion theory. Now, in valence shell electron pair repulsion theory, as the name sounds, the principle is that we know from the basic knowledge of bonding that the bonding of electron happens at the valence shell. Bonding of electron happens with the valence electron. Now, the theory, as the name sounds, explains that in the valence shell, the electron repel each other. The electron does not want to stay with each other, so the electron repel each other. So each group of electron or valence electron around a central atom is located as far as possible from the other to minimize repulsion. So the electron, if for instance, we know from basic, we will be using hybridization in explaining this. We know from basic rule that if you have a 2s orbital and you have a 2p orbital, you will not have, let's say you have a 2s2 and a 2p2. You are supposed to have the electron in the ground state to be in that form. The electron that you have should be, you cannot have the this electron pair and you have it like this. This is wrong. So it's supposed to be as presented in the form of this. Now, in valence shell electron pair repulsion theory, the theory now says that this electron here is promoted there, is repelled. It's far away from each other. So you will now have your electronic configuration to be in that form instead of it to be in this form. So this will now undergo hybridization. This will now undergo hybridization. This expression, this one here, will now undergo hybridization. But before we go to the hybridization, let me quickly explain further that a group of electrons is any number of electrons that occupy a localized region around the atom. So the group of electrons can be a single bond, a double bond, a triple bond, a lone pair, and all the likes. Those are groups of electrons that you can have in a valence shell electron pair repulsion. I will stop here, and in the next class on Wednesday, by the grace of God, I will explain the hybridization principle, and we'll use that to explain the valence shell electron pair repulsion theory that occurs in hybridization. So I will meet on Wednesday by the grace of God.